Hey everyone, and welcome to today's Explainer. We're jumping straight into one of the most foundational, completely mind-bending experiments in the history of quantum mechanics. If you're fascinated by those rare moments in science where our entire view of reality just gets flipped on its head, you are absolutely going to love what we're covering today. So picture this for a second. Imagine you've got a handful of tiny solid balls, and you throw them at a crystal wall. Naturally, you'd expect them to behave like, well, particles, right? Just bouncing off in random, predictable directions. But what if instead of bouncing, they acted like ripples in a pond? What if throwing those tiny balls actually produced an interference or diffraction pattern? I mean, it sounds like magic, but this exact phenomenon completely defied classical physics and shocked the scientific world. Okay, let's dive into this. Here is our roadmap. We're going to start with the big question. Trace the chain of discoveries, look at how it worked, check out why diffraction occurs, scale it up with the cricket ball analogy, and finally wrap up with the quantum takeaway. Section 1. The big question. So here was the massive contradiction that had all these brilliant physicists stumped. Electrons. Everyone firmly believed they were just tiny particles of matter, but when they passed through or reflected off a crystal, they produced a diffraction pattern. According to classical physics, that is absolutely impossible. Particles bounce, waves diffract. If you're relying entirely on classical mechanics, seeing an electron beam diffract makes zero sense. And yet, there it was, right in front of them. Section 2. A chain of discoveries. You know, physics really ping-ponged back and forth on this one. First off, light was considered a wave. Easy enough. But then the photoelectric effect comes along and proves light actually acts like particles, photons. So light is a wave, then it's a particle. This gets to Broglie thinking, and he pitches this wild flip side. What if matter acts like waves? It sounded crazy, at least until the Davisson-Germer experiment literally proved it with electron diffraction. We finally arrived at this incredible conclusion. Both matter and radiation exhibit wave-particle duality. Section 3. How did it work? Check out this setup. It's super elegant and housed entirely inside a glass vacuum vessel. Up at the top, you've got a filament and an accelerating voltage, which creates and shoots an electron beam straight down. At the bottom is our target, a piece of nickel crystal. And over on the right, you'll see a movable electron detector mounted on a track. By just sweeping that detector around to different angles, they could count exactly where the electrons were ending up. Now, that's really interesting about this is how straightforward the actual steps were. Step 1. The electron gun fires off the electrons. Step 2, a potential difference accelerates them, so their kinetic energy is just K equals EV. Step 3, that accelerated beam smashes into the nickel crystal, and because the crystal's atoms are arranged in perfect, evenly spaced planes, they basically act like a natural diffraction grating. Step 4, the detector measures the bounce, and rather than a random smooth spread, they hit these strong maxima at very specific angles. Undeniable proof of diffraction. Section 4, why diffraction occurs. Let's zoom in a bit and see what's actually happening at the atomic level inside that nickel. See those yellow dots? Those are the perfectly spaced atoms making up the crystal planes. When the incoming electron waves hit these planes, represented here by the red lines bouncing off, they reflect. But the waves hitting the deeper planes have to travel just a tiny fraction further. So, when they all bounce back and recombine, they can either completely cancel each other out or amplify each other in what we call constructive interference. But here's the catch. To get that constructive interference, conditions have to be absolutely perfect. And that's defined by Brogg's law, 2d sine theta equals n lambda. D is the spacing between the atomic planes, theta is the angle, n is the order of diffraction, and lambda is our electron wavelength. Because the tiny gap between the crystal's atoms perfectly matched the minuscule wavelength of the electrons, the crystal acted as a perfect grating. That's why the detector found those intense, specific spikes. And this brilliantly illustrates de Broglie's entire theory. He'd already given us the formula lambda equals h over p, which just means wavelength equals Planck's constant divided by momentum. When Davisson and Germer ran the math on the diffraction pattern they found, the wavelength matched de Broglie's prediction exactly, literally a perfect match. The theoretical math and the physical reality aligned flawlessly. Section 5. The cricket ball scale. All right, a totally fair question to ask right now is, if solid matter behaves like a wave, why don't I see everyday stuff diffracting? Let's compare our microscopic electron to something we know, like a cricket ball. Let's say it has a mass of 0.16 kilograms, flying at 30 meters per second. We can use that exact same de Broglie formula, lambda equals h over mv, to find the ball's matter wave wavelength. We plug in Planck's constant, divide it by 0.16 times 30, and what do we get? We get 1.38 times 10 to the negative 34th power meters. I mean, that is unimaginably small. Because Planck's constant is so tiny, any macro object with normal mass has a wavelength that's so unbelievably short, it practically doesn't exist. You would need a crystal with atomic gaps just as ridiculously small to diffract it, and obviously that doesn't exist. That is exactly why we only see these spectacular quantum effects at the microscopic level, and why you'll never see a cricket ball acting like a ripple in a pond. Section 6. The Quantum Takeaway. If you only take away one thing from this explainer today, make it this statement. The Davisson-Germer experiment proved decisively that electrons can behave like waves. It effectively closed the loop on a huge theoretical debate and laid a completely rock-solid foundation for quantum mechanics. A great practical rule to keep in your back pocket is this simple relationship. The smaller the momentum, the larger the matter wave wavelength. The key takeaway here is that when a wavelength becomes comparable to atomic spacing, that's when quantum effects like diffraction suddenly step out of the math and become totally visible to us. So, we've seen how light acts like a particle, and how solid matter, like an electron, acts like a wave. It completely shatters our intuitive grasp of reality, doesn't it? Which leaves us with this final thought. If both matter and radiation have this dual nature, what else in our massive universe is currently hiding its true nature from us? Thank you guys so much for joining me on this explainer. Keep questioning everything, and I'll catch you next time.